Rafi. I'm from Weill Cornell Medicine. I'm director of the Ansary Stem Cell Institute and Division Chief of Regenerative Medicine. The title of the presentation today, Stem Cell Innovation that will change the world, Part 1. So hopefully the presentations that is going to be shown that how we're going to change the direction, the translational potential of a lot of the mesenchymal stem cell, vascular biology, and prenatal and natal and fetal potential to the clinical setting. We're going to have a lineup of luminary speakers that they are going to give 10 to 12 minute talks, and at the end we're going to take questions. We're going to start. The first speaker is Dr. Camillo Ricordi from University of Miami Diabetic Research Institute. Camillo.
Thank you. So I'd like to start with the disclosure slide because everything I will be talking about potentially has commercial interest. I'm on the scientific advisory board and I have option or patents in several of the things we'll be discussing. So to start setting the challenge of the problem, we just completed the phase 3 trial of FDA phase 3 trial sponsored by NIH for islet transplantation to treat the most severe cases of diabetes, where you have severe hypoglycemic episodes and hypoglycemia unawareness, and you have the best results that now can be obtained in some of the top centers of this alliance are shown here from Ashe at Penn. You can have now virtually like 90% graft function and survival at 7 years. That is like unheard in previous era of islet transplantation. Like if you, I don't know if this is a pointer also, but anyway, the red line is the Edmonton trial that some of you know, and the line above is what you can achieve today. The results and the manufacturing and everything is online, and all the SOPs are available, open access on Cellar4. Now, so how do you start this movie? Because I don't have a pointer. Is someone?
Jason, can you start the movie?
Okay, one of the things that are most exciting for the field now is, islet transplantation is limited to organ donation, so we can have a few thousand transplants, but the key issue is when we will have technology to perform transplants of insulin-producing cells without anti-rejection drugs, then the problem will be how do you get enough cells to treat all the millions and hundreds of million patients that may benefit from this procedure. So we're very lucky to be collaborating with Doug Melton Group and SEMA, that is one of the company that is trying to build this technology to generate unlimited source of insulin-producing cells from embryonic stem cells or from iPS, from the patient own. And this is there are several other initiatives similar to that, like ViaCytes and others. The other huge development that we are working on is on how to regenerate insulin-producing cells from the native pancreas, so avoiding cell transplantation and transplantation altogether. So you could do in vivo stem cell therapy, like triggering progenitor cells from the human pancreas to become new insulin-producing cells. And this is something relatively new, but still you have the problem of overcoming rejection and autoimmunity to be able to regenerate effectively insulin-producing cells from the human pancreas. The approach that we are working now in Miami and collaborators around the world is how to engineer an implantation site for insulin-producing cell products by engineering like an endocrine pancreas in the abdominal cavity, what we call BioHub project. And we use adult islets as the standard cell therapy, but thinking that this, whatever is developed as optimization of the transplant site and immunomodulation, induction of local tolerance, or conformal coating nanoencapsulation to protect the cells, will be applicable also to stem cell product and the new generation, next generation that is in the pipeline of products that will be unlimited. So we recently published both in diabetes, and in the New England Journal of Medicine, the first cases of bioengineering an endocrine pancreas in the abdominal cavity. This has been a very exciting experience, and the first time that you can reverse diabetes in a site that is not the liver, that has been traditionally used for islet transplantation. But the challenge that now we have in the field, no matter is islets, adult islets, or stem cell-derived product, encapsulation, or macro devices, is the problem of oxygen delivery, hypoxia, and how to achieve an effective angiogenesis and neovascularization at the site of implantation. Here you see on the left, you have islets in this biologic scaffold in the omentum alone, and the blue is with a trichrome stain. You can have an idea of what you have lost early on in the graph, so that we know now that you lose around 60% of the islets that you transplant, like you lose them in the liver, also in the omentum, because of the hypoxic level that the cells see in this site. So if you put them in the kidney renal subcapsular space that you can do in rodents, they see oxygen levels similar to what the islets see in the native pancreas, and they all survive. But as soon as you put them in an ectopic site, where there is a subcutaneous, intramuscular, omental, or liver, you see this effect of the blue deposition of fibrosis and collagen. So to the right, you see early testing that we are doing now, how you can improve angiogenesis and vascularization while protecting from ischemia revascularization injury the cell that you have transplanted. And in this case, we've used Lipogem, that is a system to obtain like a stromal vascular fraction and microcluster of adipose tissue that contain all the cell element and maintain the niche of MSC pericytes and other stromal vascular fraction component that you transplant in a very microcluster kind of tissue, similar to islets as volume, but that will allow you to obtain a very strong neoangiogenesis while protecting the tissue. And this, here you see on the right, you see one of such cluster, and besides the adipocytes in orange, you see a myriad of other cells that comprise the stromal vascular fraction component, that in this case we don't separate because you don't need to do intravascular injection, but you just put at the site of transplantation. And this span from earlier work by Ventura and others, showing that if you transplant this cluster of Lipogem after ligation of the femoral artery, you can prevent losing a limb for ischemic changes. And that was surprising because it shows that this effect is not just locally, but is not just on angiogenesis, but is also protecting the tissue before the new blood vessel grow. And one of the reasons for this distant effect are related most likely to exosomes that are secreted by this microcluster and the cells comprised. And we think that practically what you transplant is a factory of exosome and MSCs locally that then can diffuse in the tissue next. And you see a difference in exosome content if you use non-enzymatic methods or enzymatic methods. In the case, the white bar is with Lipogem-derived cells, and you see the exosome content that is clearly higher. But then we started also testing the effect if you have islet plus exosome as far as glucose-stimulated insulin release and how this is significantly improved. So it's not just an effect on angiogenesis, but it's also an effect on islet function and survival. So the other big area that we are very interested, we're working with Norma Kenyon and her team at the DRI, and now also Diego Correa that joined us from Cleveland, is to try to analyze and understand and standardize mesenchymal cell products that can be derived from the fat, from bone marrow, or from other sources, and try to understand the difference between transplanting recipient, donor, or third-party allogenic MSCs, because commercially it makes sense to use allogenic cell product that can be ready on the shelf, but unfortunately the reality in our system is that MSC actually don't prevent rejection if you use third-party MSC, like they're immunogenic, they can induce allosensitization, and so that you see the difference, like donor MSC may have a little prolongation of survival, but no insulin independence, that are the white bars, while if you use recipient MSC in the lower graph, you see insulin independence long-term that continues. So we still need to learn a lot about what will be the best source of cells of MSC or stromal vascular fraction, lipogem, or tissue to favor survival and induce also immunomodulation besides angiogenesis, but it's definitely a very exciting field. And I'd like to acknowledge all our funding entities from NIH to JDF and collaborators as Scripps, REMED, Marta Garcia Contreras, who did a lot of the exosome work, and Norma Kenyon and Diego Correa for the mesenchymal stem cell work. And you'll find more of the details on the standard operating procedure and manufacturing protocols on CELAR for open access. Thank you.
We're going to get the questions at the end. So if you have any question, please write it down, and then we can integrate all the questions. The next speaker is Dr. Graca Almeida-Porada from Wake Forest Institute for Regenerative Medicine.
Thank you, Shahin. So I'm going to talk about the new perspective, how we can change the world or the world of patients through fetal therapies. Congenital diseases account for a large percentage of pediatric hospital admissions. Early treatment could preclude onset of structural and metabolic damage during gestation. For instance, in enzymatic disorders such as Leishman or Niemann-Pick or the neurogenic forms of Gaucher, the neurogenic damage that occurs in these patients during fetal life is such that it cannot be corrected even with the best therapies after birth. So the early treatment could preclude this damage. We also can avoid the morbidity associated with postnatal transplant. We can induce tolerance to the donor and exogenous protein that would allow us to have a donor for that patient if we cannot cure the disease later on after birth. So we could use that donor to provide a boost. Moreover, and most importantly, the psychological and financial benefits of the birth of an healthy infant. So you may wonder if prenatal transplantation is viable or feasible, and it is a clinical procedure, has been performed in more than 50 patients to date for 14 different genetic disorders. It's minimally invasive, and there's no reports of adverse events, and poses a minimal risk both to the fetus and to the mother. Our group is very interested in treating hemophilia A prior to birth. And for those of you that are not very familiar with hemophilia A, I'm just going to briefly summarize. It's an X-linked disorder, and these patients have a mutation in factor VIII, and that means that they cannot clot their blood, so they bleed. The treatment costs around $20 million per patient in a Western country in which these treatments are available. So the treatment right now is replacement proteins. But 75% of people in the world do not have access to this treatment. So they will die bleeding. 30% of patients that are treated in the US and in other Western countries still develop inhibitors to the protein, so therefore they cannot respond to treatment, and that poses a serious risk of death. This disease is a very good candidate to be for patients to be transplanted prior to birth because prenatal diagnosis is feasible. Digital PCR allow us to detect free DNA of the fetal DNA in a mother, so we can test that fetus just by doing a peripheral blood collection in a mother. So we can diagnose the presence of a fetus with a mutation at as early as 8 weeks of gestation. If we are successful treating these patients, we can have an infant that is healthy and does not need further treatments. If not curative, even a modest increase of factor VIII, severe hemophilia is less than 1%, while a mild is more than 5%. So if we can increase these patients to have circulating levels of factor VIII then more than 5%, that means that will not bleed, or they will only need replacement protein if they are going to have a major intervention. And furthermore, we could induce tolerance to factor VIII, and therefore, even if these patients need treatment, they will never develop inhibitors. That is the most serious complication of the treatment of hemophilia A. So I'm going to show you how we are tackling this problem and how we are developing a cell and gene therapy base for these patients. So the first question that we had was, how can we determine the optimal cellular vehicle for delivering this factor VIII protein for prenatal therapies? So we chose three different cell types: bone marrow mesenchymal cells, amniotic fluid, and placenta stem cells. Then next, we know that these cells produce some factor VIII, but we knew that would probably not be enough to achieve the levels of factor VIII that we needed to be in circulation after transplant. So we decided that we have to do a cell and gene therapy approach. So we determined what was the best factor VIII transgene for delivery with a lentiviral vector. Then we isolated these cells under GMP conditions and evaluated for parameters, for safety parameters, and also for factor VIII production. Then we had to use a fetal model of transplantation in order to see if this therapy was safe. So we used a sheep fetal model that has been used to determine the safety parameters of the first transplants that were performed in utero many years ago. And then we evaluated by different techniques the production of factor VIII in these animals after they were born. So factor VIII is a protein that is very difficult to produce. It's very big, and it can cause toxicity in the cells. So knowing a cell that has low levels of factor VIII but can indeed produce the protein would be a good thing, so we know that we wouldn't have cells that after we transduced would die because of the stress of producing that protein. So here you can see on your left, that bone marrow mesenchymal cells, amniotic fluid stem cells, and placental stem cells all produce low levels of factor VIII, but placental cells actually have the needed machinery to produce this protein at high levels. And then on the right, you can see these cells after transduction with a vector that has been deleted, so is a modified factor VIII, and that placenta cells actually produce higher levels when transduced with the same vector when compared to the bone marrow or the amniotic fluid stem cells. The phenotype of the placental stem cells have been described by many authors, and our cells have the same phenotype. And one thing that is important is that these cells express von Willebrand factor, which is a protein that associates with factor VIII to stabilize its half-life. We next tested in collaboration with Chris Doring and Trent Spencer at Emory that provide us with these modified vectors. We tested 3 different lentiviral vectors with modified forms of factor VIII, and we found, as you can see on bottom right, that the AMCO form of lentiviral vector, when cells were transduced at the same MOIs, had higher levels of transduction. And here we looked at the secretion of the factor VIII production in these three different cells, and you can see that AMCO as well produced the higher levels of factor VIII in the supernatant that was what we were looking for. So therefore, we had a cell that was optimal, we had a vector that was optimal, and then we tested in vivo in our animals. So these cells were transduced at a MOI of 7.8. This is the copy number, 0.35. The cells were producing 27 international units of factor VIII by 10 to the 6 cells, and they were transplanted at 65 days of gestation, is the equivalent of 17 to 18 weeks in a human fetus. And this is the outcome after the animals were born. On the left, you can see the percentage of factor VIII above the normal in the animals that were transplanted. So we were able to increase the levels of factor VIII by between 40 and 80%. What's important that these levels were stable up to 7.5 months after transplantation. And this is a large animal model, so you can see the increase in the plasma volume. And here on the right, the increase in weight. So right now the animals are around 50 or 60 kilos. So the weight of a teenager. And you can see that on the left, that the levels of factor VIII have been maintained throughout these 7.5 months post-transplantation. So in conclusion, prenatal therapy with placental cells engineered to express an optimized variant of factor VIII results in curative plasma levels of factor VIII following birth in a large preclinical animal model. And we believe that this novel therapeutic platform will change the world for hemophilia A patients. And I would like to thank everyone that participated in this work, the support of the Wake Forest Institute for Regenerative Medicine and our director, Tony Atala, the co-PI on this project, Chris Parada, our collaborators at Emory, Trent Spencer and Chris Doring, and the students that did this work, Nadia, Sunil, Brad, Alsheim, and Brady. And of course our funding through NIH, and this is not isolated. We are trying together to treat these patients before birth, and right now there's 2 clinical trials that I want to bring your attention to. One out of Karolinska Institute is a clinical trial for patients with osteogenesis imperfecta, and the other one is out of UCSF, is a in utero treatment of alpha thalassemia. So we believe that fetal therapies are the future. Thank you.
Thank you, Graca, for that great presentation. As I mentioned, if you have any question for those audience who just entered, please write your question. We're going to have sufficient time to ask questions. The next speaker is Dr. Doris Taylor, from Texas Heart Institute.
Thank you. I'm going to do something completely different. I was asked for this session to really talk about innovations in cell therapy and also things, how we might build an endless supply of blood vessels. And as I was thinking about regenerative medicine and where we're going and what I do, I tried to put those 2 questions in a context. So that's what I'm going to do today. And so I'll start with saying, the major reason and the holy grail in trying to build a vascular supply is because right now, tissue engineering is limited, cell therapy is limited. We transplant cells into injured regions of organs and tissues, and they fail. And they fail to a large degree because we don't give them food, clothing, and shelter. Duh. And an unmet need, though, is to build complex organs. And for those of you who've been to this meeting for years, and for those of you who've been around the Wake Forest Institute of Regenerative Medicine and other areas, you know that we can build simple tissues. You know we can build blood vessels. You know we can build a windpipe. You know we can build a lot of cosmetic organs and tissues and simpler tissues, but we can't yet build a complex organ. It's because we can't feed the cells. So that's what I'm really going to talk about for the next few minutes. And actually, before I do that, I'll just point out here that although we continue to transplant slightly increasing numbers of organs every year, and the ability to transplant organs from living donors is now a possibility, we still have a huge unmet need. And we talk about that every day where I am, which is the Texas Heart Institute. And at the Texas Heart Institute, which is Dr. Denton Cooley's house, we've spent the last 50 years trying to build an artificial heart. And for, I would say, 45 of those last 50 years, it's been about trying to build a mechanical artificial heart. But what we're really focusing on now is trying to build a bioartificial heart, because I believe the future is about building a live organ that can respond to physiology. That being said, we can't do that if we can't feed it. And the heart is obviously a very highly vascularized organ, and therefore one of the best places in the world to consider trying to build an endless blood supply. And so when you're thinking about an unmet need, I really think about the world very simply. You have two options. You can either build it, or you can use what already exists. And we've chosen the use what already exists approach, which is to take the organ you want, in this case the heart, and to actually strip it of its cells to create an organ with a vascular supply. So the strategy in my group is twofold. Give nature the tools and get out of the way. And all you've got to do is go online to look at anything, and this happens to be a leaf skeleton. And there are all these recipes online for kids, for art projects, about how to create a leaf skeleton. Well, the reality is you're creating a leaf vascular supply. And if you can create a leaf vascular supply with a little baking soda and water, maybe you can create an organ vascular supply with not much more. And so, hard to believe, but a decade ago now, my group developed a method to allow us to decellularize whole organs. And the bottom line is we tried shampoo, baby shampoo, soap. And now, one of my favorite stories is I live in Texas now, and in Texas, we derive most of our organs from pigs and humans, and most of our scaffolds. And in Texas, barbecue is a big deal. And so I get this phone call from a young woman who's a teenager, and she said, "My family is doing a pig barbecue. And you know how to decellularize organs, and so my family gave me the heart, and it's in the refrigerator. How can I decellularize it?" And I said, "Go to the drugstore, buy some baby shampoo, wash the heck out of that heart, put the baby shampoo in water, push it through over a couple of days, and let me know what you get." And she called me back and said, "This is so cool." And the reality is, it's simple enough that anybody can do it, even somebody who's got a pig heart stored in a fridge at home. So give nature the tools and get out of the way. But really, I therefore say the step one to building an endless blood supply is find a highly vascularized organ or tissue and remove the cells. And on the left, you see a pig heart where we did that, and you can see the images of the cells. In the middle, you see a movie, an OCT of the LAD of that organ. And you can see as the camera, the circle you see is a camera going down the left anterior descending coronary artery. And you can see a branch of that artery, and across the bottom you see an image. And my cardiology colleagues said to me when they first saw this is one of the most beautiful vessels I've ever seen. Maybe we need to decellularize plaque. And we've talked a lot about how an in vivo use for this might evolve. But on the right, you then see us infusing blood, and this was our very, very first human organ, so it was a very crude approach, but infusing human blood into a decellularized human heart, just to show that it was possible. And then so step two then is, the endothelial cells are probably the cells that are most your own. They're the cells that if they see the blood supply, they're going to be recognized as foreign very quickly, and we all know that. So really, step two is repopulate that vascular supply with autologous cells. And Camillo just talked about autologous mesenchymal cells, but I would say autologous endothelial cells are as or more critical. So we've actually taken the vasculature and we've infused endothelial cells either from an arterial or venous approach, and you can see in the top middle panel that the cells, CMFDA is a green dye, only live cells take up the dye and fluoresce. And there's eNOS, which is a marker of active endothelial cells. And then in the middle panel on the bottom, you see that we injected dye cells on the arterial side, dye cells on the venous side, and they met in the middle. And we got vessels that actually had cells from both. And then on the right-hand side, you can see that we have large and small diameter vessels. The endocardium is lined, and even the trabeculae and venous tree is full of cells. And on the far right, you see red and green cells throughout the heart. So the bottom line is we can not only create a clean vascular supply, we can repopulate it. So you could argue we have an endless blood supply. When we actually put blood through this organ, it flows through the whole circuit and it's non-thrombogenic. So we've published these data in PLOS One, and we've published a more recent version using liver coming out very soon in PLOS One. And you can see here now, in theory at least, that we can take one of these and we can transplant it. And when we transplant it, and you unclamp the aorta, that's a pretty good indication that there's an intact vascular tree there. And we continue to be able to take these and transplant them and get a reasonable outcome. So I love this slide, and I always like to inspire students, and it says, don't think outside the box, think like there is no box. And the reality is, we then said, okay, what can we do with these? We're working on building a heart, but building a heart is not going to be the first step at a regulatory agency. They're not going to, they don't even know how to deal with simple tissues, much less whole organs. So we've had to educate the regulatory agency, and along the way we've said, let's derive what we can from these vascularized structures and use them for research. So one possibility is a valve, and on the top you see one of our heart valves actually in a bioreactor actively working, and we can actually use the vascular supply to the annulus, not only to decellularize but recellularize that valve. And then on the bottom you see two images, one in a rat heart, one in a pig heart, of our revascularized but not parenchymal cell containing cardiac patches, reendothelialized cardiac patches. And what you see in the graph is that if we sham treat animals in green after an infarct, there's no improvement. But if you look at the blue, you see the animals actually decline. In blue, the animals decline. In green is a patch alone. And a patch alone will stabilize the infarct and actually allow stabilization of the scar and regeneration over time. But what was even more cool is when we started adding cells back, you can see we get more than an additive effect. And in fact, one of the things we've been able to show, and these data have been submitted for publication, is that we can use 10 to 100-fold fewer cells that are needed for cell therapy under the same conditions and get a significantly greater effect. So if we provide the cells the right environment, food, clothing, and shelter, basically a milieu, they do well. More than that, we can also take this, transplant it, and this is a re-endothelialized heart. You can see there's nothing in the parenchyma that we transplanted heterotopically, so next to an existing heart, and you can see in this video in the operating room, this is in a cow, that in fact cells are, you can see that the blood supply is flowing into the entire parenchyma. Okay, and it's actually, if you, in just a second, you'll see at the end, the whole bed is full of cells, okay? That's cool, that's great. So we can get a vascular supply, it's non-thrombogenic. But what's really cool is if we come back a month later. If we come back a month later and you look in the top left image, that's what you see. And then when we take that apart, we start seeing an in vivo recellularized organ. So nature is doing a lot of this work for us. So maybe we don't have to figure it all out. Maybe nature can figure part of it out for us. And I don't have time to show you the slides about new muscle and the histology of all that, but it's beautiful. But let me spend 1 minute talking a couple more slides about updates and advances in cell therapy and how it applies. So the world of cell therapy is changing. There's new science coming out that is beginning to suggest, as Camillo showed you and as Graca showed you, that cell derivatives or viruses may work even better than cells themselves. And that's not surprising, and they're also more controllable. So the future is going to be exosomes, microRNAs, viruses, the things cells secrete rather than cells. And we're finally understanding mechanisms. I've spent the last 10 years biobanking human cell products and evaluating them and correlating them with outcomes. And we've found that it's not stem cells that correlate with improvement. It's all the other 95% of the cells that are present in a cell product. And then finally, the regulatory agencies are getting it. The NIH is getting it. New laws are coming about, and I have mixed feelings about these, but I want to talk about it just 1 minute. There's right to try legislation that has emerged in Texas, and if you're not aware of this legislation, be prepared, because Congress is trying to pass this at the federal level, and I'll come back to what that is. And then there are new regenerative medicine advanced therapy designations that are allowing these strategies to move forward quickly. And finally, that means new trial designs. These products are complex and heterogeneous, and the same product is defined differently simply based on how you measure it or who's got the IP on it. A mesenchymal cell is not a mesenchymal cell is not a mesenchymal cell. The active agent in all of these studies is not a single entity. They're heterogeneous and complex. The cells we give are also present in the body. And so we're affecting the ones that are there as well as the ones we give. And then biologics are dynamic and they change. And that makes for complex trials and approval pathways. And cells have failed as a result. So oops, I'm going the wrong way. I apologize. Let me show you one thing. Refractory angina, a need for an endless blood supply. Refractory ischemia is an easy thing to treat in the heart with cell therapy in theory, because you can grow new blood vessels. And in fact, the Act 4 clinical trial showed an improvement in angina at 6 to 24 months. But the clinical need then moved forward into a larger trial, the RENEW trial. But you know what? That trial designed by the regulators had to have 2 placebo arms. And it cost so much and slowed enrollment to such a degree that the trial was abandoned, even though there was an improvement in therapy. And so the first cell that could have been approved for heart disease failed. Not because the trial failed, but because the company said, we're not paying for this, and stepped out of the business. We've got to change that. There are now expedited programs, the RMAT designation, and then finally this right to try legislation, where in Texas now there is a bill that says a patient is eligible to access and use an investigational stem cell treatment if the patient's physician has tried other things and the physician prescribes it. That is going to change the world of treatments. But we have to remember these treatments are forever. We're trying to treat the underlying injury, not the symptoms. We have a higher burden of proof. And then finally, I'll just say, although my summary is the field is moving forward, the real summary is trust your crazy ideas. And I went way over, but I thank the Texas Heart Institute and my staff. Thank you.
Thank you. Thank you, Doris. The next presentation was supposed to be with Dr. Adrian McKemey, but Dr. George Smith has kindly agreed to replace Dr. Adrian, and he's from IQ Stem Cell Center, Smith Stem Cell Center.
So you've heard a lot of really cool things, new medical advances, things that are coming, but medical advances aren't sufficient to actually benefit the patient. Clinical advances aren't sufficient to benefit the patient. There needs to be a lot more innovation that's going to occur to really help patients. And to do that, you also have to make sure the company can make money, economic benefits. So, right now we think of, to benefit the patient, we need the science, we need the clinical trials, we need the regulatory pathway. I can't tell you how many times I've seen really safe and effective drugs fail for reasons outside of safety and efficacy. We just heard one of those before. But what is coming, and with the advent of commercialization and the continuation of that, hopefully very rapidly, is the economics. And that needs to be really pulled early, and there needs to be a lot of innovation to allow these things to actually benefit the patients. So a couple little things to where there needs to be a lot of things occurring over the next 1 to 2 decades is in the area of reimbursement and manufacturing. So I'm going to touch on a couple trends we're seeing and future states where we're going to make sure these things can actually help. So in manufacturing in the future, we're going to have a dichotomy, either robust, localized manufacturing or centralized manufacturing. Now, right now, there's a lot of focus on centralized manufacturing because you can make things cheaper. So you can have greater economic benefits, greater profits, more things go to the patient, more incentives for funding to follow up and go to the patient. And that's great. And we're starting to see some large investments by manufacturing. But if this is going to really work and really bring down the cost of everything, we need to see other things like manufacturing cooperatives and joint ventures and such. These tend to work very well for allogeneic, but not necessarily for autologous. So imagine you're a patient who needs an autologous therapy in Michigan, some areas of Michigan or Montana in the winter. You can't necessarily get your cells flown out and flown back in without losing the cell product. So it may actually end up being cheaper to fly the patient from Billings, Montana to wherever the facility is and keep them there for 6 weeks. Maybe a quarter of the cost to actually do that based on the risk of destroying the therapy because you can't get the thermal shipper in. Now, for autologous, there's really cool things starting to happen. And my dream for hyper-localized manufacturing is bedside. You have a box, you hook the patient up to the box, put some cassettes in, and anybody can do this. You stick one tube in one arm, you stick the other tube in the other arm, you press a button, 24, 48 hours later, you've just delivered gene-modified cell therapy with no intervention whatsoever. These things are happening but whether it's the true bedside or the hyper-localized or the regional localized, this is what you really need for autologous cells and treatments to really take off. So we're seeing a lot of deal flow toward the autologous right now, and that's because we've seen a lot of success, the CAR Ts and such like that. But there's going to be price pressure pushing those down, $500,000 a treatment course, not necessarily sustainable in the long run in a broader sense. Are we going to see allogeneic products be backups? Money, capital, payers, there's a lot of incentive, and how they naturally think is allogeneic. So for autologous to really survive, we need a lot of manufacturing innovation to push those forward. And the other area where we need to see a lot of things change, particularly in the US, this is a little more US-centric because they're behind in many ways, is the ability to maintain getting value for your price. All these therapies have tremendous value. If you can get a good fraction of that back, you're going to be very successful. The problem is how much of that value can you actually achieve back? So we've got in some future states where price premium, especially in the United States, has a moderate erosion, or state 2 is where it just falls away, and the only way you can charge a good margin is on the ultra rare diseases. Some of the, the retinitis pigmentosa gene therapies and things like that. Or what we think it's going to happen is more a middle state, in sort of the state 3, where hopefully we can still capture price premium for rare disease, but things like diabetes, cardiac, osteoarthritis, they're going to be much more commoditized in 20 years. So to actually enable us to keep making these, commercially successful, we're starting to see pay-for-performance deals and risk-sharing deals. These need to succeed. These need to not only succeed, they have to be very robust. They have to work for both parties very, very consistently. So if you start to see a couple of failures on these, and it's going to prevent standardization and broad uptake on these, and then you're going to see price reductions or forced price reductions on the companies. Value. It's showing the value and evaluating the value of your therapy. So, what's the value of being able to see for the rest of your life? How do you judge that? But in the United States, that value generation evaluation is normally capped at 2 years or less. So if you have a lifetime cure, but you have to show all the value within the first 2 years, it's a problem. Fortunately, Europe and other areas do this much better. So are you going to start seeing insurance pools or payer pools or the government stepping in to help provide, provide insurance for the payers? Now, we're probably going to start seeing these in the ultra-orphan, but if we don't see these move to the rare diseases or larger indications, we're not going to be able to really implement a lot of these lifetime cures on a reasonable level. And we also have to be able to show your value and prove it, and not just, which means elements like valuation standardization. So the United States is fragmented. Europe is better, still somewhat fragmented, but the United States is all over the place. We've got groups like ICER who are trying to start set standards, but that's going to be a long time. But if you don't know how to show your value, you can't do it. And then you need to also do that during clinical development. Traditionally, value is shown in real world past market, but you've already set your prices. And are you going to be able to set a $500,000 or $300,000 price, or being forced to 80 or 70 or 80 grand? So that means in your clinical development, you need to prove value. That means in phase 3 pivotal trials, you have to focus almost more on the payer than the regulatory agency. So quality of life, healthcare offsets, patient-reported outcomes. For starting at the very beginning in phase 1, when you first touch the patients, you have long-term follow-ups. Instead of your long-term follow-up being a safety, it needs to be a value generation. It needs to be a real-world evidence generating thing. Maximize every single data point you can, because that's how you're going to set your value and be able to actually set a reasonable price in the future. So right now we think of it really as efficacy, clinical, and regulatory, but as the decade progresses, regulatory is becoming the speed bump. The payer is becoming your hurdle.
All right. Thank you so much for the presentation. I'm going to end by showing some few slides about to integrate some of the data that was shown about angiogenesis and the role of endothelial cells. There has been not much vascular biology in this symposium, so I'm going to show some data, what we are doing, and integrate what Doris said, what other speakers said, and that endothelial cell transplantation for tissue-specific organ regeneration. So what we heard this morning was angiogenesis-dependent, perfusion-dependent function of endothelium. But what is emerging now that endothelial cell, similar to mesenchymal stromal cell, may provide growth factors that we call angiocrine growth factors that can promote organ regeneration. In fact, each endothelial cell in each organ are different. There is a huge heterogeneity. Mesenchymal stem cell also heterogeneous, but that has not been studied as well. It's very difficult. And endothelial cell, by producing these growth factors, suggests that they're not just passive, they can promote and orchestrate regeneration. In fact, if you look literature, there is a significant amount of publication. Endothelial cells in the liver produce Wnt. They produce many different growth factors that promote liver regeneration. In the lungs, it's the same. They produce EGF, MMP14, and they produce lung regeneration. In the heart, it's very exciting. As Doris mentioned, when she puts the endothelium back, there is better contractility. It's not just because of perfusion and oxygen increases. Endothelial cells produce agrin, neuroregulin, thymosin that promote cardiac regeneration. This goes on and on and on. In every organ, angiocrine instructive function of endothelial cells promote choreographed organ regeneration. Our group and many other groups has some like mesenchymal stromal cell. Why not transplant organ-specific endothelium into injured tissue, let them engraft, produce the right growth factors, and promote organ regeneration? So this is the whole idea is that you have ischemic heart disease, diabetes. Maybe if we can identify and engineer organ-specific endothelial cells, we can transplant them intravenously or in a scaffold, let them home to the injured organ and graft, or not even engraft, produce this angiocrine factor and promote organ regeneration. And in fact, there are many publications has come out. This is Jason Butler, who was a postdoc, is independent now. And he has shown that if you get endothelial cells, put hematopoietic stem cell, they expand, they self-renew, and there are many publications has shown that the angiocrine growth factors produced by endothelial cell allow this regeneration to take place. In fact, this study that was just published showed if you get a group of mice, give them lethal irradiation or sublethal irradiation, close to 50% of the mice die because the vascular niche is damaged. If you transplant endothelial cell, they home, they go to the vascular niche in the bone marrow, they engraft, they produce the right growth factors, and you get 100% recovery of the mice. We have also collaborated with Hans-Peter Kim. We went to large animal model. We took the bone marrow of the monkeys. Half was expanded, the stem cells were expanded by M-Cherry labeled hematopoietic cell. The other half was GFP labeled and was expanded on vascular niche. Then both of them were frozen down, competitive transplanted back into lethally irradiated monkeys. The endothelial expanded stem cells outcompeted conventional hematopoietic cell, suggesting that the vascular growth angiocrine factor arms these hematopoietic stem cells to engraft better. Based on that, this is going to be the first endothelial transplant in double cords, where one cord is going to go into patient. The other cord that is not as good is going to be expanded on endothelial cell, and then the expanded hematopoietic cell plus endothelial cell are going to be transplanted into the patient with the hope to improve engraftment and enhance neutrophil recovery. And we have gotten FDA for this, and this is going to start within the next few months, and this is going to be the first allogeneic endothelial transplant, and after this we may go to autologous. But another area that was discussed here is this is endothelial single-cell transplant. How about, as Doris showed, whether we can enable the scaffold, the organoids, by better endothelial population. The problem right now, the commercially available endothelial cells are not organ-specific. And a lot of things you need a scaffold that is tough, expensive. A lot of these endothelial cells are not stable. They don't anastomose in vivo for a long time. They lack adaptability. So what's the solution? How can we do that? And Matrigel, that a lot of people use, cannot go for FDA. So we have developed a technology where we can put 3 transcription factor or one of each, ETV2 fly-ERG, on any type of adult endothelium. It brings them back to the embryonic state, not IPS. This just brings them to endothelial state. And as you see here, this enables endothelial cell to last much longer. And you see at the lower panel, these tubulized endothelial cell. And I don't have time to show. You can put perfusion. They can engraft. And in fact, if you put it in mice for 10 months, these human endothelial cell engraft, and they're anastomosed to mouse circulation. So they are durable, reliable, and become organ-specific. In collaboration with Paulo the copy that is going to present some of this data tomorrow, we have shown, for example, this ETS endothelial cell can vascularize intestinal organoids. And this is important because these endothelial cells penetrate into the organoids. That's very important because if it doesn't penetrate and talk to LGR5 intestinal stem cells, it's not going to work as shown here. And Paulo is going to elaborate on this tomorrow more, but with Alexandro, they have also put this, as Doris shows, in decellularized intestines, and it's going to go in more detail, and they put this in, and it shows they're functional. One of the areas that we have in cardiac, as Doris shows, endothelial cell can enable better cardiac function. So we took a postnatal cardiac and we put with our ETS endothelial cell. They commingle together, and endothelial cell now enable cardiac contraction. What you see over there is a vascularized, contracting myocardial cell. Without ETS, it doesn't happen. If these form large structure that beat and they're vascularized. So if you implant this, they immediately can anastomose. The cardiac cells are getting nutrition. They're getting signals or angiocrine factor to be coordinated. And in fact, if you look, they form large structure that beat. And not only that, the calcium fluxes, as shown here, is very active. So endothelial cell enable proper calcium flux on the myocardium as well. Without endothelial cell, there is random and non-rigorous contractions. So I think the future direction of endothelial transplantation is becoming more exciting. But if you want to succeed, I cannot get heart endothelium transplant for pancreatic regeneration. We have to generate organ-specific endothelium. I would argue for mesenchymal cell is the same. You cannot just transplant bone marrow mesenchymal cell and say, oh, it's going to work for brain. Mesenchymal cell also in this organ is different. But we have made a huge stride to engineer organ-specific endothelium at top ETV2 fly-ERG. GATA4, for example, has shown can get this generic endothelium, make them into liver endothelium, so we can transplant those. So I think we have entered an era where we can get these endothelial cells, transplant them, hopefully, into large damaged myocardial cells, or put them in decellularized, as Doris showed. And hopefully, this actually is science fiction right now, shown here. But the title was Modern Medicine. So I think we have entered an era of translational vascular medicine. Vascular niche renders executive function in organ regeneration by producing angiocrine factor without fibrosis. I think we are generating generic endothelium for transplantation. And I think in the next few years, maybe we can mix mesenchymal cell organ-specific with organ-specific endothelial cell, put in on decellularized organ or transplant them and do that. And I think we are very excited for the first in-human endothelial transplant. I think this is more challenging than mesenchymal transplantation. I mentioned all the people who have done the work, and this is the conclusion of our presentation. And I ask the speakers to come to the podium so we can start the question and answer session. Thanks for your attention. So I would like to ask the audience if you have any question to start to ask from any other speakers, any questions that is in your mind. There's a question right there. Just one and then here.
Hi, this is a very basic question. Can we get access to these presentations? Because it's been a bit fast and, little difficult to catch up.
I cannot hear you. I don't think it's working.
Now you have to speak up.
No, I was wondering if you can get access to these presentations, the PowerPoints.
PowerPoint presentations?
Yeah,
Yes, I think you can.
Okay.
You have to talk to the directors, I think.
thank you.
There's a question in front here. Question.
Shahin, this is actually directed for you. You mentioned at the end the combination of possibly using organ-specific mesenchymal cells with organ-specific endothelium. Can you talk a little bit about how you think that sort of crosstalk would happen and what the role of that combination therapy is?
It's on.
It's on, yeah. So I'm going to, this is for the whole panel, but I start to say that I think mesenchymal stroma cells, I have an issue with calling them stem cell as of yet because I haven't seen any single cell transplantation to prove that. But these mesenchymal stroma cells produce, I call it mesangiochrine factors that are totally different from what endothelial cell produce, what monocyte inflammatory cell. Each of these cells produce different growth factors. So I think just saying that we're going to transplant endothelial cell and have the right growth factors, I think is too simplistic. To build an organ, as all the speakers mentioned, we need all these parts. So if you have a major myocardial damage that both the vasculature, the stroma, the extracellular matrix is damaged, I think eventually to rebuild this, you need both mesenchymal stroma cells, you need the inflammatory cell, and you need the endothelial cell. So I think the crosstalk between all these three would be important to have a successful long-term form organ.
If I can add, I think one of the interesting things, I completely believe that you don't need the single cell types, but what we were fascinated by the results using lipogem or microfragmented fat is that you maintain the niche where you have the pericyte, the endothelial cells, the MSCs, and the activation of the secretome that you see following this manipulation is almost like if you pre-activate the tissue that you implant. So we're trying to understand why when you put these cells in joint, you regenerate cartilage. If you put them in a soft tissue that if ischemic, you regenerate blood vessels. And we are lucky because in a way, islets are a microorgan, so we're just dealing with 2,000 cells at the time. But the effect that we're seeing are really encouraging.
I think this is on. I want to make 2 points. One, we've got some data that suggests that there are specific endothelial progenitors that can be used in multiple places throughout an organ, but if you take the mature cells from a given organ, they actually have tropism, so they go to a specific region in that organ depending on where they were derived. But the progenitors do a better job of actually dispersing and becoming mature throughout the organ. But I also want to say that when you look at cell therapy, and you look at cell therapy in the heart anyway, most of the effects that have been positive at the border zone, at the region where the niche is most normal. And when early mesenchymal cells were transplanted in the heart, they gave rise to bone, cartilage, all the things you would expect if you put mesenchymal cells in a scar. So I think we have to think about environment. Stem cells respond to their location. We know that. That's why they're stem or progenitor cells and not mature cells. And so we have to consider the location too. And I think, and then I want to speak to the point you made about cost of goods. I think there are a lot of people at this conference who can impact cost of goods, all the reagent. What makes this so expensive is all the reagents that go into creating these cells or growing these cells. It's not about whether or not you can get enough cells. It's about whether or not you can get enough cells for less than $1 million.
And also in terms of cost, if we have to mix endothelial progenitor cell in an organ-specific manner with mesenchymal stroma cells or other cell types, I agree the cost is going to go up, but we learn from CAR T cell therapy, if the drug works, each of the CAR T-cell for a patient may cost $435,000, and I don't know whether insurance company are starting to do that, but if it works and you save lives, I think is practical. So if we can want to rebuild the niche, and it's expensive, but if it works, it's worth the cost, and I think it's going to
As long as CMS buys into that, but right now, that's a big.
But I think we're going to be cheaper than them.
Well, you're going to get a lot cheaper, but when you're treating a couple hundred patients a year, great. When you're trying to treat 50,000 to 100,000 patients a year, the thought is going to be completely different. And part of it is when you're developing these drugs is the better your cell, the less you need. So right now we're putting 10 to the 8th cells in. Well, what happens when you can make it 10 to the 5th cells? Well, you've just dropped your cost of goods 90%, There's a lot of ways you can control it during clinical development and the scientific development that will make a great impact. If you think about it now, you can make a big difference early.
And also have the courage to challenge how much you can charge over your cost for a therapy, because I think some situations they go away with murder because FDA now doesn't regulate pricing. So it's like you approve a product or a therapy, and then it's the Wild West. Let's see how much we can get for this therapy, so that this doesn't happen in most of the rest of the world. And I think we have a lot to learn and have the courage to change the system.
The NIH and the FDA together held a Regenerative Medicine Institute workshop a month or two ago, and the goal was to actually ask these manufacturing questions. It was a great 2-day workshop, but there are going to be a lot of RFAs and a lot of data coming out from that. So keep your eyes open for that, and if you can get access to any of that workshop online, I highly encourage you to do that, because these were the questions that were discussed.
Any other question from the audience? There is one question here, please.
Hi, Doris. Excuse me, Eric.
Oh, sorry, there's one.
Thank you. I enjoyed very much the session. I was just wondering if we should concentrate more on immunology, in the sense that autologous is going to be difficult, particularly on large number of patients. And I just wanted to know what you thought are about allogeneic, and if that is a possibility at all for the future.
Well, in our case, what we love about autologous in the lipogen system is that you take a mini liposuction, it's point of care, it's hundreds of dollars, it's not $100,000 of dollars, and will change, I think, healthcare for a lot of soft tissue orthopedics. If you inject in cartilage, you regenerate cartilage. If you put in femoral head necrosis, you regenerate bone. You put in an ischemic situation, you prevent ischemic injury. But that is a very simple, that I think for point of care kind of application, you can apply autologous. And for our purpose, I like it because for regulatory is minimally manipulated, is autologous, and will not add the complexity of have multiple products. So since my lifespan is limited to the next few years, having passed 60, I don't look for green bananas, things that may work in 20 years. But I think it is very important to work on all these other complex advanced cell therapy model, combination product, because that's the future for new generation, for young kids like Doris and the rest of the panel.
I think that you are correct. I mean, we have to work on immunology, because if you want to do off-the-shelf allogeneic, because it would be maybe a cheaper source to go and more controlled source to go, we have to look at immunology. Mesenchymal cells are privileged, or not so much, but at least they don't really elicit the immune response. They may be destroyed over time. But if you go to endothelial cells or other type of cells, we really have to look at immunology and type of cells that we are using for each organ, or for each, because endothelial cells are different from each organ, and they can elicit an immune response that is different from what we know about mesenchymal cells. So we have seriously to look into that if we want these cells to engraft and remain in the organ.
And I want to mention that the field of not pluripotent, but direct conversion using transcription factor is getting a lot of momentum. Our group has shown you can get endothelium, turn them into hematopoietic stem cell. You can put transcription factor, make hepatocyte. So I think that's going to get momentum. But then you're going to say, how about autologous iPS? I want to mention, when you make iPS-derived cells, epigenetic memory is erased. And many of the minor determinants, including HLA-1, are epigenetically reprogrammed. So it's not completely going to be out there whether autologous iPS is going to be completely immune privileged. They may still mount an immune response. And this is important because, as you know, a week ago, it was released information from Japan Times that one of the patients who got the iPS pigmented epithelial transplant in the eye, they developed severe edema to the point that the pigmented epithelium has taken out. That could have been a scaffold issue. It could be because that was allogeneic, mounted an immune response. But if the autologous has minor determinant issues, you're going to get the same problem with autologous iPS. So I think we need to work with autologous iPS and also direct conversion of our own adipose-derived cell. I think is also, the cost may be more, but I think that can help us with autologous as well.
But I just want to say with direct conversion and a lot of these conversions, as I was taught in pharmacology, every factor has an effect you know and one you don't. And a lot of these direct conversions have the potential to create cells that we may not want to deal with down the road.
That's why I love exosome and microvesicles, because a lot of the stem cell effects are mediated through exosome and microvesicles, and there you may have even advantage on the immunology when you use autologous iPS.
And I just want to point out that when we compare exosomes for males and females, ours are superior.
Yes, I had no doubt about that.
But I want to mention that's completely total point, but I didn't have show the slide, but we have been able, if you find the right transcription factor, we showed that you can get an adult endothelium, turn it into authentic hematopoietic stem cell that engraft forever without leukemia. The problem with iPS and ES is that they are stuck at the pluripotent stage, and since 1973, since we discovered and we were able to grow mouse embryonic stem cell, we have not been able to push these cells beyond embryonic stage, so there are disadvantages, but I think the research has to go through that.
So just a thematic comment. I mean, over the past 10, 20 years, you know, we've done things that seemed impossible. So don't think about, identify problems, don't think we can't solve them, because everything we've done has solved the impossible. And just, you know, the immunology is a great area where we need to push, but just because you don't see it now doesn't mean that you can't do it.
One question.
Yeah, hi, Doris. I'm Eric Eller, and I had the opportunity to be in your lab about a year ago. And for those of you who haven't seen it, it reminded me very much of something Tony Stark would have in one of his movies. But I actually had two questions for you, and one of them is when do you realistically think you would see someone basically ordering a heart? And the second piece was, I'm not sure that I heard you right, maybe you could clarify it, that you said that you were using 10 times less cells than people were using in MSC therapies these days and having better results. I was wondering if you could expand on that.
Yeah, so what we found with regard to dose is that if we load an extracellular matrix-based patch with cells, either because we increase retention or because we change the niche in which the cells find themselves into a healthier niche, we get a beneficial effect with about 10 to 100-fold fewer cells than we need if we inject the cells alone. And it persists. So we're looking at mechanisms as we learn that exosomes and other things are having an effect. I think it may be that we're changing the secretome of the cells by giving it a healthy niche also, and they persist. In terms of people ordering a heart off the shelf, you know, nature has a way of fighting back when you get close. That being said, I'm more optimistic about our science right now than I've been in the last 5 years. And I think in the next 2 years, you're going to see some pretty exciting things happening, at least at the level of congenital heart disease, if not adult hearts.
One question, one quick question, and that's it.
Thank you. This is a question for Dr. Graca, Almeida-Porada. So we have seen a long-term effect of the factor VIII, and you stated that with prenatal therapies we could induce tolerance, which is fabulous. And I wonder if this could be related to the actual cell type transplanted. It has the placenta, derived cells or stem cells. And an additional small question, any issue with chorionic gonadotropin released, any hormonal imbalance?
The fetus at the time of transplant is an environment that is mostly tolerogenic. The immune system is not developed yet. So, and the T cells and the B cells that exist and the thymus that is developing, will see any cell or any protein that is introduced at that time as self. So the immune system is going to be educated towards that protein or towards those cells from those donors and see it as self. So if you introduce hematopoietic stem cells at that time, even from, in a allogeneic setting, those cells are going to be mostly engrafted and then they will persist. So it's the environment of, during development of the immunology of the fetus that will allow cells or proteins to be engrafted or to be delivered, and then the fetus becoming tolerant. The thing is that we have to maintain those levels throughout gestation and even through births, otherwise that tolerance can be lost. But if you maintain, and that has been demonstrated for transplants for hematopoietic stem cells, that if we maintain around 1% levels of engraftment, the donor-specific tolerance will be maintained.
All right, I think in that note, as you see, we are really changing the world. We're getting close. So in that note, I want to thank all the speakers for that elegant presentation and all the questions. And we finalize this session. Thanks for your attention.